Okay, so thank you all for coming and welcome to the January 2025 Howard Astronomical League General Meeting. We have a packed agenda tonight, some interesting, very interesting speaker that I'm super excited about, and an exciting election and all sorts of good stuff. Good to see you, Sundar. Let's see. I'll begin the meeting. Before I do, I want you guys to take a look at the slide that's on the screen. And can anybody tell me if there's anything different from the slide that was on the screen at the last meeting? Has anything changed on that screen?
The date.
The date, yes, I was just going to say.
I think I see some hydrogen alpha that wasn't there.
The date is
And
correct.
25 years.
There you go. Howard Astronomical League is now 25 years old, actually 25 years and a month. So congratulations to anybody who's been here the whole time. I don't know that anybody's been here the whole time, but if you have, congrats. And I hope we can make it another 25. Let's make it to the next Halley's Comet visit. Okay, so anyways, I'm pretty excited about being the president at this momentous occasion. Our agenda for tonight, we'll go through some introductions, some club business announcements, have our speaker talk, and then our special what's out in the sky this month. We only have a what's up in space section, and Wayne will do that. And then we'll go through images and sketches and maybe have a little time to pivot around at the end of the meeting. So first introductions, is there any, you don't feel obligated to if you're shy, but is there anybody in the room or online that is a new member that would like to say hello?
Hi, I'm a new member. I'm Stanley Max. I teach at Towson University, and I learned about this organization through Steve Rifkin. So hello, everybody.
Great, welcome. And your affiliation with the school, is it astronomical related?
No, I teach math. So, you know, since
All right,
astronomy uses math, it's related in that way.
all right, good.
Very good. Excellent. Yeah, thank you.
All right, thank you. Welcome to the club. And also thanks for, we saw you at our planning meeting the last time, and thanks for jumping in and getting engaged right away.
Yeah, good. You're welcome.
Thank you.
Oh, yes, somebody in the room.
Yes, my name is Cliff Bowen. I heard about this organization from Marty at Company 7.
Excellent.
I was down there purchasing my first telescope, which I'm waiting for to come in a couple of weeks. Excited to be here.
Fantastic. And
What telescope?
Skywatcher 10-inch.
nice. You went to the right place to buy a telescope.
I realized that.
As you know by now.
Yes, several hours in, I realized I was in the right place.
Yeah, good. Do you bring a power bar with you when you went in there? And
I will next time. I hope Marty's not on it.
yeah, sometimes he shows up. Who knows? But great. Welcome to the club. And you know, I think what you'll find is that there's lots of people here who will be maybe not quite as vocal and talkative as Marty, but you'll get lots of people that'll be very, very helpful and willing to, you know, if you come to some of the events, it's a good place to share knowledge and whatnot. So welcome. Awesome.
Thank you.
Okay, so unless anybody else would like to say anything. Okay, so let's move on to the agenda and club business. So the first thing we have is wow, that is it is 1 year old date there, but make 2023 into 2024. This is the treasurer's report as of the end of last year. Well, Joel Goodman, who prepared and usually delivers this report, is on an airplane right now. So Jim Tomney offered to go through the slides. Is that still good with you, Jim?
Yes, it is. I'll go ahead and share if you want to. It says
I pasted the slides in if you want me to just do it.
Oh, okay, well then just, yeah, just walk through the slides. All right, so we can see that our bank balance has gone up year over date, year to year, which is always a good thing. Next slide. And this talks about the membership statistics. You know, not a whole lot of change here. I think we continue to be very healthy in that regard. You know, a slight uptick in membership, and a lot of that has to do, at least the board feels, due to our outreach public Star Party events. They almost always, you see a bump in membership following successful Star Parties. So, you know, kind of encourage everybody to help continue to make our Star Parties a success in 2025. Next. All right, a little hard to see, but here is the breakdown. You can see that our income between the 2 years held about steady, went up slightly in 2024 compared to 2023. The spending, however, decreased significantly from 2023. We had larger outlays, I think, especially the observatory was involved with that. And again, anyone is welcome to attend the board and to provide their input. But in general, the board feels that, you know, using this money to keep the HALO in really good operating condition is an important factor. Something else that we did do this past year was that we decided to try the C-Star loaner program. The jury's still out in terms of how successful that is or not. You know, but we're going to try to be innovative within reason with our budget to help keep interest going in HAL. The next slide. Okay, and so this kind of talks, kind of helps break down those purchases a little bit more. So the major purchase in 2024 was a new flat screen in HALO, which I haven't had a chance to see yet, but I understand is really excellent. The purchases in 2023, we were in strong need of a new laptop for HALO, so we got that. And you can see also hard drive. The C-Star was purchased, and also an iPad and accessories for the C-Star. So those account for the higher expenditures in 2023 compared to what we spent in 2024. And next. Oh, okay.
Do you
So-
have, is that it? Do you have anything else?
In terms of the treasurer's report,
Yeah.
no, not really. I would just simply open it up to see if anyone has any comments or questions.
I have a comment, and that is that the, you know, if anybody has good ideas on, again, as Jim's mentioned, the board meetings are open to everybody, anybody that's a member. So if you have ideas on what we could be doing with that money, let us know. We tend to be conservative. We're thinking about a rainy day when something happens to the dome or the shutter or something, and we have the funds, you know, available to do the repairs and whatnot. But we feel like the equipment in the observatory is in pretty good shape right now. But you know, maybe we're missing something. So anybody has any ideas, please volunteer them.
And
Yeah.
the observatory, I just want to say, being in good shape, I think, you know, a tip of the hat to you, Victor, and also to Dale. I think you guys have been really good in terms of assessing things and pointing out when things need to be replaced or upgraded, rather than letting it reach a crisis stage. So again, you know, thanks to you guys for being good stewards of HALO and helping us to keep it in good shape.
Thank you. Okay, so at this point, I'd like to turn it over to Jim Johnson. Oh, I'm sorry. One more question.
Question, suggestion.
Oh, suggestion.
So currently you guys have the C-Star S50 program.
Yes.
Do you guys consider getting one more if the waiting list is more? or some other kind of telescope in that same range, the new ones that came up, so that you will have these two lunar scopes.
So I
and
have,
reduce the wait list.
we have like, I think we need to be a little more proactive about reminding people about the wait list. Because there was a couple of months, or either that or we need to change our strategy in terms of how we exchange between users each month. Because there've been a couple of months where the people on the list didn't show up. I have it with me tonight, the C-Star. The idea is to hand it off to the next person on the list at the monthly meetings. And there've been a couple of meetings where it just sat idle for a whole month. Yeah, so I don't think at this point, we need to just get our procedures down a little smoother. Because it doesn't seem like we're even getting it fully utilized. So,
The follow-up question is, if it is lying idle with you, would you consider loading this to someone who is present in the room?
yes, I need to remind myself and look at the list right now. But if that person, the next person that's on the list is not here, then by all means, I'm happy to hand it over to you if you want to take it for the
Yeah.
next month. Yeah, that's why I brought it in the car.
Thank you.
Yeah.
That's a good, comment.
It's, yeah, well, after the meeting, let's go out and we'll hand it off.
Thank you.
Okay, thanks, Sundar. Jim?
I think you probably want to give it to Wayne.
Oh, my gosh, Wayne, I am so sorry.
All
I'm
the
sure
habits die hard.
If Jim wants to do it, I'm
Jim
not
has
gonna
run the
argue.
election. You're here, you're in front of me, you've done this for so many years that my brain just went to you. So yeah, Wayne, I'm sorry, please take it away.
So this is the day for our annual board elections. And so I'm Wayne Baggett, and I was asked to be the election committee chairperson today or this month. And I don't
Sorry.
see anything but your background.
Yeah, I'm sorry. My bad. I was trying to turn the volume up here.
No.
It's coming back. Go ahead.
Okay, so next slide.
Are you seeing it now?
I'm seeing it now. Next slide. Can you hear me?
Yes. Are you seeing our screen?
Yes, I am. Can you go to the next slide, please? Okay, so from the HAL leaders in particular around this time of year, starting in about October, roughly, you start hearing a few phrases such as, it's your club, help make it what you want it to be, and HAL doesn't run itself. And this is all in the lead up for the elections that we're going to do tonight. And so, next slide. So for the it's your club, make it what you want it to be. To do that, you need to do things like listed here, running for elected office, which is what we're in the process of doing tonight, offering to assist with HAL efforts in outreach or in-house projects. You can become a key holder, certified telescope assistant, or certified telescope operator. You can suggest speakers for our meetings, and you can submitting suggestions, to the board for activities or club improvements, similar to what Victor just requested, that if you have any ideas, please let them know. The second sentiment, however, depends on members doing the first, because we need to have officers and leaders who are going to help HAL be successful in the projects for the year. So I want to take some time now to recognize the people who, I'm going to say, quote, led, unquote, HAL in 2024. Next slide. I'm going to start with last year's election committee of Jim Johnson. Thank you very much, Jim, for your efforts in getting us a board of officers to run the club for the year of 2024. And that board was, as you can see the list here, Victor Sanchez as president, Jim Tomney as first vice president, Grace Coventry as second vice president, Joel Goodman as treasurer, Dana Porter as secretary, and David Stein as the events coordinator. So let's give them all a big hand. Okay. Next slide. The board has the ability through the bylaws to appoint a few board members. And Victor Sanchez was appointed to be the observatory director. Ken Saul was appointed to be webmaster. Hannah Broder was the publicity chair and ran our social media, primarily Facebook and Instagram. Steve Jaworski is our astronomical league coordinator, and Crystal Rowland is the librarian. So those are our appointed board members, the observatory director, and God, I want to say webmaster are actually voting members and the others are not. So let's give them a hand. Thank you very much for your service in the last year. There are other people who help in executing plans put out by the board, in particular, Jared Case, who's the Discord channel administrator. So all of you who are on the Discord and are familiar with, for instance, the object of the month, Jared set up the Discord and runs it all the time. And the board also set up a web development team to improve our website. And there will be more information about that coming in the hopefully near future. And that consisted of Satish, I'm going to mess this up, Naliyapan, Stephen Prebut, and Victor Sanchez, with help from various and sundry other people. So thank you to those.
Yes. And yeah, Wayne, you haven't seen my charts, but yes, there will be some information coming up in the very near future.
Okay, next slide. And we also have, as I mentioned earlier, certified telescope operators, and I'm not going to go through the whole list here. But these people operate the observatory during our public star parties and occasionally outside of our public star parties, during members only star parties and such, and impromptus. So they provide in particular a highly visible interface with the public during our public star parties. I couldn't find a list, but we have had certified telescope assistants who are basically certified telescope operators in training. So they can't operate the telescope alone, but they can operate the telescope under supervision of a CTO. In addition, we have key holders, which includes all the CTOs plus this additional list of people who provide the host duties for our public star parties and member star parties. And they also call impromptu star parties in between those scheduled events when the skies are clear and or people ask for them. And then finally, there are all the club members who participated in HAL activities in 2024, in particular the public star parties, because the public star parties are probably our most important activity outside of these meetings that we do. So give a hand to all of those people. Thank you. Next slide.
And I'd just like to mention, sorry if I could, Wayne.
Yeah.
If you are interested in becoming a certified telescope operator and you've been a HAL member for at least, what is it, 9 months? Is that what it, then that's another way where, as Wayne is saying, you can reach out to me, to whoever's the current observatory director, and we'll set up training sessions and kind of instruct you on how to use the gear and go through the whole process.
Okay, next slide. Thank you. So let's get on with the elections. So the HAL bylaws state that we will elect officers every year in the month of January, and its results are by a simple majority. If there's only one nominee for any office, the election for that office may be by voice vote. And if there's but one nominee for each position, a single voice vote may be held for the entire candidate slate. And so because we have only a single candidate for each position, we will use a voice vote for the entire slate. So there's just one vote here to be held. So voting, I didn't have written down here, but voting is restricted to members. So please, only if you're a member will you please vote. And if you have a family membership only gets one vote, irregardless of how many people are registered under that family membership. You only have one vote. And so we'll vote by raising hands. And if Jim Johnson would count the votes at the RNC. I would appreciate that. Thank you. And on Zoom, if you go down to the bottom of your screen, there's a React link or pop-up. And at the bottom of that, at least on my version of Zoom, there's a raise hand. So just please raise your hand when you do it. Please lower your hand if you just raised it, because we haven't started the vote yet.
Oh,
Thank
sorry.
you.
I
So
saw I saw raised hands and figured I should get over there.
no, not yet. So I'm going to be a little bit weird here, and I'm going to ask for those opposed to the slate to vote first, since hopefully that'll be an easier number to count. So if you will, then we can go to the next slide. And so here's the 2025 board members election slate. We have Victor Sanchez to continue as president, Jim Tomney to continue as first vice president, Grace Coventry to continue as second vice president, Joel Goodman continuing as treasurer, Richard Taibbi is a new candidate for secretary, and David Stein will continue as events coordinator. So we're going to have just one vote for this entire slate all at once. So as I promised, those opposed, please raise your hand. Remember, online, do the react and raise hands. Okay.
Are we still on the nays?
I'm sorry.
Are we still on the nays?
No, all I'm seeing is the background, the Milky Way, without
Oh.
any H alpha.
Sorry, my bad.
Okay, there was one person I saw. Was that an intentional thing? Because I see it gone now. Are you so opposed on the Zoom link? Okay. Lost my mouse. Golly. Jim, are you ready to move on?
Yes,
Okay, so now the vote is all those in favor of this slate. I see some people online who are physically raising their hand. Okay.
I wonder what they see now.
I think I got a number there.
If you intend to vote yes, now's the time to raise your hand.
Sorry, I have to scroll through the list of participants here, so it takes me just a moment. Please keep your hand raised. Re-raise it if you lost it.
Steve, are you abstaining on purpose?
No, I'm just having some trouble finding where I can raise my hand. Oh, there I am. So there's my hand raised. I'm enthusiastically raising it.
Oh, I guess I can raise mine. Sorry. So busy counting. Okay, I have a number.
Wayne, we have 8 votes in the room here.
8 in favor.
Yes,
Were there any opposed?
no,
Okay, then I guess by essentially acclamation, this board has been approved by the membership.
Excellent. Yay.
The final vote I got was 35-0 in favor.
Now, does that,
So-
we'll have to talk about this offline if that satisfies our quorum requirement.
Well, in the treasurer report, I saw at the end of December, there was 303 memberships.
Okay, there we go. So we got a quorum too. Excellent. The bylaws state that we need at least 10% of the membership to vote.
So thank you, everybody who attended and voted. We all appreciate it. And thank you to our new board members.
All right. We'll make HAL in 2025 another great year. Thank you for doing that, Wayne.
It was my pleasure.
Okay, so I think, the appointed positions, I have a slate of appointed positions as well, but I need to get a board approval. I do not plan on being observatory director and president again next year. We have a new candidate for observatory director, a former president of HAL, who I think will do a fantastic job, but I need to vet it with the board and get the board approval before we announce that. We'll announce that at the next meeting. Okay, so now that that is done, we can continue on with our agenda. Next is our star party schedule. I mentioned this at our last meeting, but here's our the dates are out. They're posted on the website, and I also have in my possession. When I speak, can the folks online see the camera in the room when we're speaking here? Is there a little window that shows the room?
Yes.
Yes.
Okay, so we've got our new set of, I forget how many, 500 or 1,000 cards printed. The new cards have, that's the blank. The new cards have the dates of all our star parties, along with some information about HAL. So I have all the cards here. I'll populate the little boxes at the observatory. For those who are in the room, you're welcome to take one or more if you want to hand them out to people. If you're going back to Company 7, I always give Marty a bunch. So if you have a plan to go back there anytime soon, maybe I can give you some to hand off to him. Anyways, so usually on this slide, I mentioned the dates, and hey, there's Chris Todd with his hand raised. Would you like to say something? Or is that still from your vote?
No, I just forgot to lower my hand. That's all.
Oh, okay. Yeah, I didn't let the cat out of the bag, but let's say the person who might be observatory director might have also recently just spoken on the Zoom call. Okay, so usually on this slide, I put the recent events, some kind of pictures or words about what's been going on. It's been so cold that there really haven't been any recent star parties. There was one early in the year. I think Jose called one, but then the weather got bad. But as usual, please keep your eye open. If you're not on the impromptu email list, you can sign up by going onto the website and just keep your eye open. This month has been great if you're a planet person, except for the atmosphere has been very, very, very turbulent. Anyways, the other bit of business that we have is that we have a new website, and it is not live yet. We're doing our final stages of beta testing. This is what the front page will look like. It looks, in terms of functionality, it's very similar to our existing website. If you look at all the menus, there's a lot of information about how, but you can click and drag down the drop down menus and find out more information about the monthly meetings and observing, imaging, blah, blah, blah. You can log in and get access to other information about the club, as well as some of the equipment and resources on the right. So I encourage everybody, we'll send out a message. One of the things that's nice about this new website is that it's written using a more modern framework. So it auto scales to mobile. It's a lot easier to see on your phone. And this little thing on the right will be like a quick reference if you want to get some information about the upcoming meetings or what's coming up in the month. And then we'll just kind of have some on this little scrolling carousel in the middle, just a few featured items of current or recent events. So hopefully it'll make it easier if you need to just get some info or find a link to the meeting and whatnot. So that, keep an eye out for that. That should be coming up soon. And I'd like to re-echo the thanks that Wayne gave to the web development team. They put a lot of, their own hours into this, especially Satish. He's been really, really very, very generous with his time.
Long time coming, and it was going to take some work. I was scared of it myself. It really looks pretty, guys. Very good. I'm excited. Thank you.
If you send me a note if you want to be a beta tester, I'll send you a link to where it is now. You can get to it, but I don't. It'll go live soon.
Thank you.
Okay. So without further ado, I would like to announce our featured speaker, Dr. Ravi Sankrit, with the Space Telescope Institute in Baltimore. Ravi has actually, I kind of was wishing you were in the room because I have one of my best friends is a professor at ASU. I wanted to see if there's any connection there. But so Ravi came from Arizona, where he got his PhD. He did a lot of work on narrowband Hubble images, including some of the original Pillars of Creation image data. And then he moved to Hopkins, did his postdoc, worked on the fuse and then worked on the Sophia mission, which I don't know if this is coincidental or not, but our speaker just a few months ago talked a lot about Sophia. It's terrible. Can anybody remember? I'm forgetting his name at the moment.
Whoosh.
Anyways, he gave an excellent presentation on Sophia, and it's just so cool that could actually work. Anyways, Ravi came back to Baltimore in 2017 and has been working on Cosmic Orion's spectrograph team, and he likes to study emission line nebula around compact stars regions. So without further ado, sorry, I just kind of read that through without any other flourishes there. But Ravi, you want to share your screen?
Sure. Thanks. Let's share that. Okay, is that working?
Yep.
Okay, great. Yeah, so thank you very much for having me on this to give a talk. And I would have loved to be there in person, but I was for 7 hours in Atlanta airport on Saturday last, where I caught something and haven't gotten over it yet. So it has to be remote, but hopefully it'll be fun. So a little bit of background about myself. A scientific background. So I did my PhD at Arizona State, as was mentioned. And before that, I was an undergraduate in India in physics. And I went for a summer school in astronomy. And it was in a different city because I was in Delhi up in the north. This was in Bangalore, which is the center of astronomy. And one of the things I learned there, we learned many things, but one of the things I learned was about the Crab Nebula and the Crab Pulsar. And what I learned was that the Crab Pulsar, which is rotating at 30 times every second, is slowing down, and that the energy that is lost in the slowing down of the pulsar is actually powering the synchrotron nebula that we see. And this connection between the physics, it's energy conservation, and this loss of energy is something we've done in a mechanics course. And so this connection between physics and astronomy is something that I found really exciting. And that's kind of my background and my into astronomy. So then I came to ASU, and continuing with the crab, I did my PhD with Jeff Hester, who was on the WIFPIC-2 instrument team developing it. And so he actually had a whole bunch of guaranteed time data on a large number of nebulae, including the Crab Nebula, including the Pillars of Creation Eagle Nebula. And so it was very exciting to work on that. And these, what I want to show here is the Crab Nebula image that was there in my thesis and one of my papers. And what I want to point out was this was in 1994. The angular resolution of the image is 0.1 arcseconds, which is amazing. So we can see this ionization structure. And WIFPIC-2 had this huge suite of narrowband filters, so you could pick up emission in individual lines in the optical spectrum. So I've showed 3 here, but we actually had 4 others, including helium and oxygen 2, and not oxygen 2, we had a few others. Anyway, so this was very exciting, and this was way back when, soon after WIFPIC-2 was installed on HST. Okay, so now moving on to the main talk. Couple of things. I sometimes go kind of slowly in these talks because I'm thinking through things, and that's fine. But sometimes I may skip something or go a little fast, in which case, please stop me and ask questions for clarification, whatever it is. So I want to keep this as conversational as possible, as flexible. There's no need to go through every last slide and every last thing I've written down. So whatever is interesting, whatever is nice to discuss, let's just go with that. So feel free to ask questions and interrupt. Okay, so what I'm going to talk about is the Cygnus Loop Supernova Remnant. But to start with, just a brief introduction to supernovae. There are 2 kinds. One of them is the core collapse supernovae, where a massive star just runs out of nuclear fuel in the center. And in a matter of a second, gravity takes over, pulls stuff in, and then the pressure is so high it explodes, and it just everything is sent out into the surroundings. The other is the thermonuclear supernova, which is either a white dwarf accreting from a main sequence companion till it reaches the Chandrasekhar mass of 1.4 solar masses, or 2 white dwarfs merging and then reaching the Chandrasekhar mass, and then the pressure becomes too high and they explode. Again, a supernova results. But what happens after that is what really creates the supernova remnant in either case, which is you have surroundings. And in the real ideal case, the surroundings are, if you want to do a theoretical calculation, you assume that it's spherically symmetric, uniform, and then you have these very well-defined stages. Initially, the ejector from the explosion sort of goes out, sweeps up the mass surrounding it. Then at some point, you get the swept up mass becomes higher than the ejector mass, and then you get a shock wave, and then you get it cooling behind the shock wave. And this is when you see the bright supernova remnants. That fades away, but you still have a hot interior, and then you're sort of driving this wave out. And then you merge into the ISM, and there's no more supernova remnant. You just have some kind of hot plasma bubble. Of course, in reality, the supernova remnant is determined by what we see is determined by the ISM surrounding it, or the interstellar medium around it. And this can be very non-uniform. So you get things in different stages and very complex morphologies. Let's see. So I just wanted to show this as this really beautiful H-alpha image where it's really difficult to pick out supernova remnants. A lot of the bright features here are really the H2 regions. There's the Gum Nebula here, there's Orion there, there's the superbubble, the Orion Eridanus superbubble down here, and various other bright H2 regions. And the Cygnus loop, which is the supernova remnant I'm going to be talking about, is kind of hidden in there. It's there, and I think it's that one. I'm almost sure it is. But if we go to the X-ray, it all looks different. Now, this is where supernova remnants jump out, even though they're small. So you see the Cygnus loop, very prominent. Cassiopeia A, which is like about a much younger supernova remnant. The Crab pulsar out there. So, and the Vela supernova remnant here. So this is just to give a background that we are dealing with this very energetic phenomenon, which is really bright in the X-rays, and we're examining it in the optical. That's what this talk is about. But this is sort of the background. So the Cygnus loop itself is kind of this textbook supernova remnant. It is very nicely seen in deep H-alpha images. It's away from the plane of the galaxy, so it's sort of set apart from the rest. But you have all these surrounding emission. And the distance has by now been pretty well established, very accurately established, based on the distance of a star, a Gaia distance of a star that's associated with one of the shocks. So if that association holds, we have a very precise distance to this object. And then we know what the diameter is, and then you can kind of get the age. And I just want to point out that this is a beautiful survey called the MDW Sky Survey, which if people are not familiar with, I'd encourage you to look at, because they've been doing these very detailed H-alpha images of large parts of the galaxy, and are very happy to share FITS files, images with people. So this is just great. On this, I pointed out two NGC objects. So before this was known as a supernova remnant, they were cataloged as individual clouds. In fact, that is NGC 6992, then NGC 6960, and I think there are few designations here. This is known as Pickering's triangle. I think it has another NGC number. But all these were known as individual nebulosities, but it was only like kind of in the 20th century, sort of mid-20th century, especially after radio observations were done, that the idea of this as being one entity came into being. So by the way, if anyone has any questions or has anything to, please interrupt, or if someone is moderating, just let me know.
That's a good point. I'm not monitoring the screen. If anybody online sees, can somebody volunteer to just, if a hand is raised, can somebody just speak up? Can I nominate you?
Yeah, I got it. And yep, and I see Harini has her hand up.
So in the picture, it says 725 PC. What does PC stand for?
So PC stands for a parsec. It's a unit of distance. It's about equal to 3 light years. So,
Okay.
725 is about 2,100 light years.
Okay, thank you.
And 42 PC again is the diameter, the same unit. So the Cygnus loop is a very popular deep sky object. I mean, there are like many places where this is seen. And I just wanted to show one just for the fun of it, because this is from my friend and colleague who works at STScI, Dave Strickland, who was also a postdoc when I was at Hopkins. He was there as well. And this is the T20 telescope in New Mexico. I believe it's moved to Utah right now. But one of the things I also wanted to show was this is just fantastic images, but with these narrowband filters, sulfur 2 H-alpha, oxygen 3, which I believe are relatively easily available these days, which was not the case, I think, 3 decades ago, 2.5 decades ago. So this is something that we have a lot of fun discussing these images. What we want to focus on is this faint filament out on the northeast limb of the Cygnus loop. And this is an image which was obtained by my advisor, Jeff Hester, and his group way back in 1986. And this faint filament, which is pure H-alpha emission right at the edge, the X-ray edge of the remnant, is what we're going to look at and focus on with Hubble. And I put non-radiative and transition shocks, and I'll come to that in a minute. But what I wanted to do was to first contrast. So this is the Hubble image with WIFC3 taken recently of that same filament 1. The red is H-alpha, and the blue is oxygen 3. On the right-hand side is another Hubble image, and this you may be familiar with as the Veil Nebula, which was a press release and a photo release by the Institute some years ago. And this is on the western limb. And what I want to show you here is how the difference between the H-alpha oxygen 3 is like so stark between these two. On the right-hand side is like a regular bright supernova remnant shock, where the oxygen 3 is kind of on the outside, and the H-alpha sort of is behind that. The H-alpha is frothy, there's a lot of turbulence, a lot of instability. The O3 is relatively smooth. And this is bright. This is one of the bright regions in the Cygnus loop. And the shock is moving that way towards the west. In contrast, the filament we're talking about is very faint, and it's pure Balmer emission, except in this region where you kind of get some oxygen 3. And I want to spend a few minutes describing that just because that's such a fascinating phenomenon.
Question in the room?
Yeah.
Question in the room?
Yep.
So it's for me. So the oxygen 3 is on the forefront of the shock wave trail. So the hydrogen is trailing it. Is that often the case? Is that something to do with the supernova, the way that it ejects the material, or is that just this particular instance?
So on the right-hand side, the trailing happens, and it's the general feature of your standard supernova remnant shock. So what happens is you get stuff that's ionized, and that starts recombining. And so oxygen 3 happens first, and H-alpha happens afterwards, essentially. So oxygen 3 typically leads H-alpha in these bright shocks on the right-hand side. So that's what's happening in these bright shocks. On the faint shocks, it's the other way around. So for Balmer filaments, the oxygen 3, which is in cyan here, is trailing the H-alpha. And that's because of what I'm going to explain next, that this kind of shock is fundamentally different from the other kind of shock in terms of how the H-alpha is created. Does that answer the question?
Yeah.
Yeah.
Well, is it, but that recombination of the ionized material, is that happening like right as the supernova is exploding, or is this something that happens later on?
This happens much later on in what was kind of like in the set-off phase. So you've swept up a lot of material, and the shock is going into the interstellar medium, and a lot of the material is behind the shock. So this happens much later, like many thousands of years after the explosion of a supernova.
Thank you.
So here's just a schematic representation of what's happening. So the shock is moving to the left into this interstellar medium that has partly ionized gas. So there's a lot of protons and electrons, which I've shown in blue and red, and there are hydrogen atoms, which kind of I've shown is connected with an orbit. So this kind of a schematic. Now, these kinds of shocks, they are magnetic shocks, so there's no collision involved. So what happens is that the ionized particles, so the charged particles sort of rotate in these magnetic fields, they get compressed and heated up. So the temperature goes from like 8,000 Kelvin to maybe about 300,000 Kelvin in shocks like these. The neutral atoms just pass through. And on the right-hand side, you get collisions between neutral atoms and protons, or neutral atoms and electrons. And very close to the shock front, sometimes these neutral atoms are not ionized, but they are excited. So you get the hydrogen going into an excited state, and that cascades down. And as it cascades down, it emits H-alpha, the hydrogen line at 65, 63 angstrom. So that is from the atom level 3 to level 2 after it's been excited. But then you also get ionization very soon after. So it's just in this very thin zone just behind the shock front that you're getting this H-alpha emission from excited hydrogen before it gets ionized. And these are much rarer, much fainter shocks, but very, very useful, as we'll see. And so this is the 3 epochs of H-alpha images using HST. So I mentioned 2 of the really important things about Hubble, which was the spatial resolution, angular resolution, and the narrowband filters. The third thing is now its longevity. It's going to be 35 years in orbit soon. And so we've been able to look at the same filament thrice. You can make out the red and the green. They've hardly moved in those 4 years when we first looked at them, the first and second time. But then when we came back in 2020 and took the third epoch with WFC3, you can see this distinct motion, about 1.4 arc seconds, which is 14 pixels, which is an enormous amount for Hubble. And so that's something that is really something you can really work with. And I think there was a press release and there was a photo release, and online, I think it was in the email Victor sent, the GIF that the OPPO people put to show how spectacular this looks. But this motion is really fantastic and we can do a lot with it. The basic thing that we're going to do, however, is to measure the proper motion. That is, how much has this shock moved in the 20 years or the 19 years between 2001 and 2020, and see what we can learn from that. So of course, measuring proper motions is like not anything that's new. And I just wanted to bring this little piece of history. Back in 1958, Minkowski talked about 6960 and 6992, these 2 nebulae on the either side of the Cygnus loop. And he says it is long known, and this is 1958, it is long known that the object is expanding. And Hubble has measured it. Unfortunately, Hubble wrote it in some Carnegie report, and it's not available on the web. Otherwise, I'd have pulled that out as well. But there again, combining a velocity of expansion that they got with the radial velocities near the center with this, they just assumed that the expansion in the sky and the radial velocity measured with lines was about the same, and they got a distance to the Cygnus loop. This is kind of what we're doing here, but in reverse. Let me walk you through this a little bit slowly. And by the way, let me know when I'm running out of time. We can sort of stop anywhere and discuss stuff.
You're good.
Yeah.
Maybe even another 25 minutes would be fine.
Yeah, okay. Just let me know. But I want to, like, this is sort of the key observational bit. So on the left, down at the bottom is 2 epochs, 2001 and 2020, showing how this shock front has moved. And we can see it's maintained its shape. It's nothing dramatic has happened. It's just moving forward. This is like a sheet. The way the geometry is, it's like a sheet seen edge on. And the brightest parts are the tangencies to the line of sight. And what we want to measure is the proper motion, as I said. And we want to measure these proper motions at places where I've kind of indicated with the blue arrow, which is the forward shock. You don't want to measure it somewhere behind the leading edge, because then these tangencies can sort of change because of rippling, and you may not be actually measuring real motion. So you really want to focus on these edges. And what our data allows us to do is to get the proper motions over these regions. So we're taking a cross cut here over several pixels, taking a projection from here to there in 12 or 13 different, how many? 4 and 4, 8, yeah, 13 different locations. We are collapsing it across these projections, seeing how much it's moved. And this is like relatively easy to do with high accuracy because of the angular resolution. So if you take this to there, you can easily measure that distance, and you can divide it by the time between the 2 observations and get proper motions. So these numbers are the proper motions in milliarc seconds per year that the shock front has moved. so you can just convert. Now, knowing the distance, as I said, we have now a very accurate distance of 725 parsecs. You can convert these proper motions to velocities, which is the shock velocity. And that shock velocity comes out to be 190 kilometers per second to 290 kilometers per second. 190 for the 55 kilometers, 55 milliarc seconds per year, up to 290 for the 85 milliarc seconds per year. So, so this is the basic measurement that we do. Now we need other ingredients to get other physical numbers. And one of them, which I want to mention, because this is kind of the other thing that I do in addition to narrowband imaging of nebulae, is UV spectroscopy, which is that from ultraviolet spectra, we can get what the densities are and what the shock velocities are in an independent way. And I'm going to show that just very briefly, not in any great detail. But carbon, nitrogen, and oxygen behind the shock, which I showed a few slides earlier, they get ionized, highly ionized. So oxygen 6 is 5 times ionized oxygen. Nitrogen 5 is 4 times ionized nitrogen. And these have strong lines in the ultraviolet. And that's the energy that the shock energy is converted to. So the shock energy is converted to these line energies. So you can get what the pressure is, and you can get what the pre-shock densities are. And so what we determine is that for 200 kilometers per second, you need a pre-shock density of about 2 hydrogen atoms per cubic centimeter in order to produce this kind of spectrum. And one of the important measures that you can get from those two numbers is the ramp pressure. That is the pressure that's driving the shock. And this is something we can think of even in terrestrial terms. You have a pressure, it drives a shock or a wind. And the other thing we can do, and this is an important piece, is that we can assume there's constant ramp pressure. And this is just equilibration of pressure that we're familiar with from just terrestrial physics, any physics. Pressure equalizes on time scales that you communicate in this pre-shock region. So if we assume that, and this is a very good assumption, we can use the difference in shock velocities to map the difference or the variation in densities in the pre-shock medium. So ahead of the shock here, shock is moving up. So ahead of the shock, you have variations in density by about a factor of 2. And if you look at two positions very close by, 0.7 and 0.8, you have a 45% variation on small angular scales. And why this is important is this is the kind of fluctuations in density that drives turbulence in the interstellar medium or is driven by these shocks. So supernova remnant shocks drive turbulence in the interstellar medium, and there's turbulence behind the shocks as well. And all of this is sort of mixed in with the fact that you have small scale fluctuations in the density. So very simple calculations, we sort of get to sort of really interesting ideas about what's happening with the injection of energy into the interstellar medium.
Another question from the room?
Yep.
It's me again. So what are the units of that density? Is that 2.2 atoms per cubic centimeter?
Yeah, it's 2.2 hydrogen atoms per cubic centimeter. That's sort of a simple way of characterizing densities. So to convert it to real density, you'd have to also account for the fact there's helium and oxygen. Those would contribute to some extent, and convert it to grams.
Okay, so when you earlier showed the temperature being 300 something thousand degrees Kelvin, that it's not like if you were there, it's not like you would you even feel that?
Very good question. The densities are very, very low, but they still have enough volume so a Maxwellian velocity distribution is still obtained. largely speaking. So the velocities would sort of be like that, but over sort of large expanses of space. So like on a human scale, there'd be nothing. It would be like vacuum.
Okay, thanks.
So now I want to take a very quick look and continue this discussion at oxygen 3, which is, as I said, trails the H alpha. So what happens is you get H alpha, you get it ionized, and then it's just about starts recombining and you get oxygen 3. And we can play kind of the same game with the oxygen 3 filaments between 2001 and 2020, where we see it's moved. It has a velocity because we know the distance. We can use the ram pressure being constant and say it's 3.6 per cubic centimeter rather than 0.95 or 2. And now this is important, that because you get oxygen 3, but you don't have H alpha in this recombined region, you can see this is pure oxygen 3. When we go back to this, there's no H alpha here, which is in red. We can get a shock age. We can say the shock can't be more than 850 years old, because if it were more than 850 years old, then you're going to get H alpha also from the brighter region, the recombining region. So you can place that limit. So that's yet another thing we find out just based on these images. One last thing, and this is a little more complicated, and I don't understand this incredibly well, but I have collaborators, especially John Raymond, who does. And so we published this paper and earlier, and here I've sort of done a simple thing, which is that if you take, as I said, a change in the velocity very close by, you're going to really sort of induce turbulence in the post-shock gas because you have this density changing very rapidly in front. But because we see this thing is so smooth and no turbulence has actually happened, we find that the turnover time for turbulence is 1,200 years, but the shock age is only 850 years. So this is consistency that the shock is very smooth. We have not gotten turbulence behind the shock, as has happened, for example, in this other shock that I showed you. Here, turbulence has taken over, whereas in our shock, it has not. So that's a nice consistency calculation that we've done. Okay. And that's sort of the last thing I wanted to present. And I wanted to summarize the results and kind of show that based on really simple calculations, but beautiful data, we get shock velocities. And I didn't mention this in detail, but we don't have any evidence for deceleration. The shock is moving kind of smoothly. We have a ram pressure driving the shock. We have density variations over 10 arcsecond angular scales of about 45%. That's probing the ISM. We get the shock age, and we get the eddy turnover time, which is longer than the shock age, which is nice because it means we have a smooth shock. So now, a couple of big questions here, which is the Cygnus loop running into a cavity created by the progenitor, which is what people thought it was? So you have this massive star, it's blown out a cavity, and it has these edges into these walls into which the supernova shock is running, which is why it looks really circular. The other hypothesis is maybe they're running into a distribution of clouds that is just typical of the interstellar medium. So things that we are doing here will help answer that sort of larger question of what kind of surroundings are there around the supernova explosion like gave rise to the Cygnus loop. So that's kind of an immediate question about the surroundings. And here it's just a mix of various different wavelengths. And the key ones are that you have dust with the Planck, gray, sort of the dark part here is all the dust clouds around. And the purple is the galax, which is the bright UV in the supernova remnant. So last slide, where I just want to kind of summarize, sort of not just summarize my talk, because I really focused on this piece here, which is the Hubble data. But kind of the big picture idea is you have a supernova going off, you have many supernovae going off. They result in these supernova remnants that stand out from the surrounding interstellar medium. You can examine them very, very closely and in great detail in a multi-wavelength way. They kind of allow you to figure out what's happening with the surroundings, and that's here, and we hope to answer those questions. And then you kind of feed it back into what this means for our entire galaxy, because a lot of the energetics of the galaxy is determined by supernovae, and it's mediated by supernova remnants. So it's this like wonderful picture that we are looking at, and we're looking at an incredible amount of physics going on, and we're doing it, and I am a Hubble Space Telescope enthusiast. I did my thesis on HST. This paper came out last year. I have new programs, and our collaborators have new programs doing similar stuff. So a lot of this is to just say how wonderful HST has been for us as well in this field. So I'll stop here and take questions and discussions. Thank you very much for the opportunity to share this.
Thank you very much. This was an amazing presentation.
Wonderful.
Would anybody online like to ask any questions? I see somebody clapping. Was that a hand raised or a clap?
So when you have all this data and these observations and this analysis now, how will you use that looking forward?
So one of the things that we will do is, so the Cygnus loop is really large, and we can look, using Hubble, we can look at only small pieces of it because of the field of view. So we actually have, for example, another program that looks at this cloud in the southeast. Some of the data that I showed on the western limb is not yet fully analyzed. Part of it has been completely analyzed, but the others hasn't. So one thing that we want to do is to try to piece together like what things look like at different parts of the Cygnus loop, and kind of say, okay, can we put an integrated picture so the pressures that I mentioned, so we can assume constant pressure when we're looking at nearby regions. So between here and here, we can assume constant pressure. But we know from observations that the pressure like there and the pressure here is different by factors of up to 5. So we want to put together how the pressure varies in different regions. So then we can kind of put together what really is the impact on a sort of supernova remnant scale, as opposed to just a single shock. So we can really think of this as a shock laboratory with different kinds of shocks at different places. So that's one piece of what we're going to do with the analysis. And this would also include data taken some time ago, maybe not Hubble, if Hubble is not available for other regions, but we have, say, X-ray or UV data. So if we get, for example, pressures and shock velocities everywhere, then we'll have a fuller picture. That's one. And the other is to look at other supernova remnants as well.
Okay. If you were to take JWST and point it at the same place, would that tell you, would you learn anything new from the wavelengths that records in?
Oh, absolutely, absolutely. And, that's all part of the future plan. One of the issues is that JWST has a much smaller field of view if we want to get spectra. So if we want to get spectroscopy of the dust. One of the things that happened, and let me give you the bigger picture here, is that these shocks, they destroy dust grains. So the interstellar medium around these will have dust. And we know, so we've looked at it with Spitzer. In fact, this region over on this side and one region up here, we looked at with Spitzer and showed that there was dust destruction going on in these shocks. And so elements were being released back into the gas phase from being in grains. We can examine that carefully in great detail with Webb. We need to figure out where exactly to point it, which instruments to use, and how exactly we're going to interpret the results. But yes, absolutely.
And my last question is, in one of your earlier slides, when you showed a reverse shock before there was the outward shock. Could you explain what a reverse shock is and how that happens?
Yeah.
Actually, Phil,
Yeah.
well, as part of that question, can I tack on my question to that too?
Yes, you can. I will invoice you in the morning.
So like as a layperson, we think we sort of understand what the word shock means, but is there a formal definition for what shock actually is? Is there something that we could understand that you can define shock?
Yeah. So shock, like in terrestrial circumstances, a shock would be created like when something is moving faster than sound. So when you want to communicate something between one point and another via if a pressure rises in one place and it's communicated to a different place by typically acoustic waves. If something is moving faster than the speed of sound, or a pressure wave, some kind of pressure wave. If
Right.
something is moving faster than the speed of sound, like supersonic aircraft, then that communication can't be done. So you get a shock wave. So you get a discontinuity where the properties, the thermodynamic properties change abruptly over a very short period. So that's what a shock is. In the interstellar case, the shocks are almost always mediated via the magnetic field because it's the field of the ionized particles, it's the speed of the ionized particles which matters. But again, it's supersonic versus subsonic. So there's a sound speed. And so the motion of these ejected particles from the supernova is just much faster than the local sound speed. So what happens is that the stuff ahead of it doesn't know what's coming. There's no communication. And so the way that the physical properties adjust themselves is over a very small region. So the definition really would be, the simplest definition would be where there's an abrupt transition in density and temperature because there's been no communication of changes in pressure.
Wow, awesome.
Okay.
And it is really pressure, like the same in a different scale, but it's the same sound. It's the pressure, the longitudinal wave of the atoms moving.
Exactly. But it would be typically of the ions moving, so it's the Alfvén velocity rather than the sound speed that sort of determines it.
I see.
Right. So let's go back. Where's the reverse shock come in?
Yeah, so now the reverse shock. What happens is, so you get the forward shock. So you have ejecta sort of filling this entire, so the ejecta move at different velocities. The faster ones go forward, the slower ones are inside. And so this bubble inside is filled with ejecta. So then when you have the forward shock piling up material, you get this higher density and this higher temperatures. And at some point, the pressure in this region that's moving out becomes higher than the pressure that's inside the bubble as it expands. Because as you expand, you're getting more volume. And this again goes back to pressure volume, Charles' law, Boyle's law, one of those, so equivalent of that. You're expanding, so your pressure is falling inside, but your pressure is rising at the edge because of the shock. And so the pressure in that shell is higher than the pressure inside. And so the shock is moving, so there's a shock moving backward.
Okay,
cool.
So that's how the reverse shock happens. And then the reverse shock eventually goes all the way to the center. And so the entire interior has been at some point shocked to some plasma, and then there's a plasma.
That's so cool.
Yeah.
Any other questions? Well, if not, I would very much really like to thank our speaker. This was a really, really cool, interesting talk. Thank you so much, Ravi.
Yep, thanks very much.
And Harini, if you're still there, the next time we're in the same at a star party or something, we can explain to you what a parsec is. It's a geometry-based measure of distance that's defined by when a star moves by 1 arc second when the Earth travels around the orbit of the sun. And so a parsec comes from parallax second. And perhaps Arjun can explain it to you. He probably already knows. If not, we'll describe it the next time we're at an event. Okay. So thank you again. Now I lost my Zoom screen. There it is. I'm going to bring it back to the other monitor. And I'm going to go ahead and share again. I really need to get 2 monitors here. Then I can. Okay, so can you guys see my screen again?
Yes.
All right. Once again, I'd just like to say thank you to Dr. Sankrit, and you are welcome to you're most welcome to stay on and hear the rest of our meeting. And we understand if you need to go, and you're also welcome. We'll give you honorary free access to one of our public star parties. That's a kind of a joke because they're all free.
Okay. Yeah. Yeah. Okay. No, I'll stick around and see.
Okay, great, great. Okay, so our next speaker is Wayne. You want to just take it away?
Sure.
So we, if anybody's new in the club, we normally have a what's out in space or what's up in the near sky, the planets, or maybe sometimes Phil does the sun. What's up in this with the sun? So in this meeting we have a what's up in outer space, and that's Wayne who will present.
So I want to talk about the status of the Roman Space Telescope, which is NASA's next flagship observatory. This Roman Space Telescope has been named after NASA's first female executive, who served as the first chief of astronomy throughout the 1960s and 1970s, and who was absolutely instrumental in getting the Hubble Space Telescope approved by NASA and through Congress. So the astronomy world owes her a big favor. And she is an astronomer. She was an astronomer, I guess I should say. So she did her job very, very well, and the field has benefited greatly from her work. So on the image over on the right-hand side, that's an artist's conception of the Roman Space Telescope. And just to get you oriented, at the top is a sun shield that protects the telescope from sunlight. The sun is over to the right in this picture. Okay, that keeps the sunlight from entering the telescope aperture. And just below that on the right-hand side are the solar panels to provide the spacecraft with power. And the spacecraft bus, that is all the electronics, the propulsion, the communication system, the power distribution units, all this kind of stuff that you have to operate any kind of satellite. The spacecraft bus is at the bottom, coated in that gold foil, the gold color. Immediately above the spacecraft bus is where the science instruments are held. And immediately above them in that kind of wrinkly tube is the telescope. It's a Cassegrain telescope. So there's a primary mirror just immediately above the instrument carrier, and there's a secondary mirror hanging out in the middle of the aperture. If your image is big enough, you can kind of see it there. So Roman is an infrared mission. with a field of view of about 100 times of what Hubble's infrared instrument on Wide Field Camera 3 is, but in that 100 times the field of view, Roman's going to have Hubble's resolution. So we're going to see a lot of the sky at the same resolution Hubble sees it.
Is that near infrared, did you say?
The near infrared, yes. The optics are not cold, so, or not particularly cold, so it's going to be near infrared. In fact, the primary mirror is the same size as the Hubble primary mirror, 2.4 meters, and it was provided to NASA by the National Reconnaissance Office. Unfortunately, NASA had to rework the mirror to make it an acceptable optical design for the observatory. So really, they didn't save a whole lot of money by having something gifted to them, but nonetheless, they did it. The telescope has a shorter focal length than the Hubble Space Telescope, which helps to produce its wider field of view. So the Roman Space Telescope is going to principally address problems with dark energy, exoplanets, and other areas of infrared astrophysics. And in particular, they expect to image greater than 1 billion galaxies and find about 2,600 new exoplanets through the use of microlensing, which is monitoring the brightness of a star. When they see it brighten in a particular way and then dim in a particular way, they can say, a small exoplanet just passed between us and the star. So they're going to do microlensing survey of the inner Milky Way because the star density is higher, so they'll have more possible targets. The instruments, or the telescope, consists of a 2.4 meter primary mirror with 2 science instruments, the primary one being the wide field imaging instrument and the other being a coronagraphic instrument. The coronagraphic instrument is principally a technology demonstrator, but it will of course make science observations to demonstrate the technology. We're going to talk almost exclusively about the wide field instrument here. The launch of the Roman Space Telescope is going to take it to the Sun-Earth L2, basically the same region of space that JWST and Gaia and other satellites are occupying, and is going to take place no later than May of 2027. And Roman has a 5-year primary mission with a 5-year extension. So the going in plan is to get basically 10 years out of it, hopefully more. And to put that in a little bit of perspective, that is exactly what the Hubble Space Telescope had 35 years ago when it was launched. It was a 5-year mission with a 5-year extension. So next slide. So the wide field imager is a 300 megapixel camera. It contains 18 detectors, 4,000 pixels by 4,000 pixels each. Over on the right-hand side, it shows there's a picture of the Andromeda Galaxy. The moon is shown there for scale. And if you look really, really closely, up to the upper left of the Andromeda Galaxy, there's a kind of pinkish square, and that is the field of view of the Hubble Wide Field Camera 3 IR imager, IR instrument. So that's how big Hubble sees with its infrared instrument. The bluish outline that's kind of big, it goes all the way to the center of the galaxy, is a big mosaic. Let me see, is Wide Field Camera 3's Panchromatic Hubble Andromeda Treasury Program, or FAT survey, PHAT. And so they use the Hubble infrared imager on Wide Field Camera 3 to do a mosaic of that much of the Andromeda Galaxy. It's an incredible mosaic if you've never seen it. Finally, the Roman wide field imager will see the white squares all in one pointing. So they will, the Roman instrument will see that much of the Andromeda Galaxy with just one observation. Okay, so it really is wide field. It's larger than the full moon. Okay, so if you look closely at the Roman, the white squares, you see there's little gaps between them. That's because,
Wayne, I'm sorry, we have a question.
oh, I'm sorry, Harini.
Go ahead, Harini.
So on the other slide, I saw it said it would take a microlensing survey of the inner Milky Way galaxy. I wanted to know what is microlensing?
Okay, microlensing. So lensing, it is a general relativistic effect where if you have a massive object with a in front of a light source, that massive object can cause the light rays to bend and actually be focused a little bit. Okay, so that's called gravitational lensing. Microlensing is gravitational lensing, but the massive object doing the lensing is an exoplanet in this case. So if an exoplanet moves in between us and a distant star, it will cause the light of the star to get brighter in a very particular way, and then it will dim in a very particular way, and so they can identify that it's a microlensing event. Okay? And they're going to be using it to identify exoplanets, not to study the star. Okay, so they're going to detect exoplanets that way. Okay.
Excellent
Okay.
question.
Thank you.
As always, it's an excellent question. So if you look again, looking at this image of the Andromeda Galaxy, the white squares, there's gaps between the white squares. That's because those are separate detectors. They're not CCDs, but they're CMOS type detectors, and you literally cannot put them right next to each other. So there's got to be a small gap, and so they will fill those spaces by dithering.
And those are the 18 squares that you mentioned, the 18 detectors. Why are they in that? Is that pattern, that shape that they're in for a specific reason? The offsets?
Yeah, probably it has to do with the image quality across the field of view produced by the optics.
Okay.
So the wavelength coverage of Roman will be basically half a micron to 2.3 microns. So basically green to near infrared with 8 filters and 2 dispersing elements. So it doesn't have the huge cadre of filters like Hubble or even JWST, but it only has 8 filters and 2 dispersing elements. So it's not a huge set of filters to choose from, but they're very powerful. And they're all pretty wide filters, so they're similar to our RGB or luminance filters. So there's no narrow bands that I was able to locate. The telescope will be extremely sensitive. It will reach 28th magnitude in 1 hour at 0.62 microns. So kind of a little bit bluer of H alpha. Okay, this stellar sensitivity is this high mainly because of the tight star images at 0.6 microns. And it's also high at 1.46 due to the extreme width of the filter. The filter ranges from less than 1 micron to 2 microns. And down at the bottom, there's a couple of images of what the star images will look like. The left one is at 0.62 microns. And at the right, that's 2.13. So almost as far red as it goes. I want to point out that these are highly stretched images, and there's roughly a factor of 1,000 in intensity between the dim red parts and the brightness the bright at the center of the star images. So these are highly stretched, and so when you look at them, they won't look like that unless you really stretch the image really hard. Okay, JWST has similar kinds of structure in its image. Okay, next slide. So I said this was a status. So let me tell you what the status is. So both of the instruments, the wide field imager and the coronagraphic instrument, the spacecraft bus, the telescope assembly, or the optical telescope assembly, and the solar arrays are at Goddard Space Flight Center in Greenbelt just down the road here. And in fact, they have actually mechanically integrated all of these assemblies. So everything except for the solar arrays, I should say, everything has been put together and it's all as one piece. Electrical integration is started and it'll continue through January, through this month. Coming up in the future, they're going to be starting system level testing when all the electrical integration is complete. And system level testing consists of what they call aliveness and functional tests, which basically makes sure that all the parts are, especially the electronic parts, are talking to each other. And these tests get run many times through this process. They will do the vibration and acoustic tests. So for example, they'll do the aliveness and functional tests before the vibrant acoustic tests, and then they'll do them afterwards just to make sure that the vibe and acoustics test didn't break anything. Okay, so that's the purpose of the aliveness and the functional tests. They'll also go through electromagnetic interference testing to make sure that none of the electronics are doing bad things to, say, the imaging detectors and putting noise into the system. And then they'll put the whole assembly through thermal vacuum tests, so make sure it can work in the vacuum of space and at the temperatures it's expected to experience. Finally, the optical tube, as you'll see in a minute, that kind of wrinkly gray thing on that artist's impression, and the solar panels will be added to the assembly in the fall of 2025. Those have to be done later because of limitations in the thermal vacuum test chamber. Those things make the assembly too big to use in the test chamber. Okay, next slide. Photos. So this is a photograph obtained back in, I think it was October or very early November, of the clean room down at Goddard. Okay, this is in what's called the Spacecraft Systems Development and Integration Facility, or as NASA likes to call it, the STScI. And this photo was taken by HAL member Dave Hickey, who is working on Roman. The STScI is Goddard's largest clean room, and it's one of the largest clean rooms in the world. JWST was put together in here, the telescope and the instruments. To give you a little orientation, there's a very, very light wind blowing through that room, coming from the right-hand side, from that wall of pink filters, which keep all the particles and everything out of the air, because you don't want particles to settle on your optics and on your electronics and stuff. And if you look at the people, you see they're in what are called bunny suits to protect the equipment from getting skin cells and hairs and things like that from the people. Okay, so I've identified the various assemblies, and if you start at the upper left, that thing way back in the corner of the image is the spacecraft bus, the thing that was gold colored. The circular item below it, I believe, is an adapter to attach the spacecraft to the top of the rocket, because there are some little rocket nozzles hanging down from the bottom of the spacecraft. So that's where all the power distribution and the communications and the fuel tanks and all the gyroscopes and things like that are on that piece of equipment. Over on the very right-hand side is the wide field instrument underneath that plastic cover. The plastic covers to help provides additional help to keep particles off of the instrument. And it also, if you notice, it's kind of gray colored because it's actually a conductive plastic, so that electric charges won't build up, because these instruments are extremely sensitive to shocks, to electric shocks. Just literally 2 or 3 volts worth of electric shocks can damage these equipment. Below the wide field instrument is what's called the instrument carrier, which is basically just a structure that'll hold the instruments into the telescope. And in fact, the chronograph instrument is actually already installed on the instrument carrier, although it doesn't show up in this photograph. And right in the middle, of course, is the optical telescope assembly. So you can see the primary mirror, the secondary mirror on its struts hanging above it, and then there's a cover over the baffle going through the primary mirror. And again, you can see people for scale. the instrument carrier will go underneath the telescope right there where that person is sitting at the bottom of the image. Okay, so this was the status in, I believe it was either late October or early November. And next slide. Notice how busy the clean room is. Here's everything put together. So again, you've got the little adapter to mount it to the rocket, and from the bottom, above that's the spacecraft bus, then the instrument carrier, and the optical telescope assembly. So it's all put together, and this was a photograph taken in early January. Okay. So what they call mechanical integration is now complete. And you can see how big the whole thing is. Next slide. And so that's basically concludes what I'm talking about, but here are some resources you can go to if you wanted to have information. And for those of you who are online, I will post them to the chat so you can get to them quickly. Are there any questions?
Wayne, I have a comment. That was excellent. That was
Thank you.
Just excellent. I love the way you put it together and explained it. I didn't know any of this stuff, and it's just great. Thank you.
You're
I
welcome.
guess this one's going to be a little less scary than James Webb when it goes to deploy. There's less mechanical machinations to get it to go and deploy.
Yeah, I'm not certain of this, but I believe the major deployments, there might be some smaller things that I'm certainly not aware of. The major deployments are the sun shield. I don't believe it's not going to be in that position for launch. I'm 90% sure. And also, I think the solar array is in 3 parts and it's got 2 little wings that will fold out, I believe.
Well, cool. Thank you so much for sharing that. Anybody have any other questions? If not, I'm gonna just move on to members' astro photos. But I want to skip to the end because I'm just in love with this picture. So I'm just gonna. So I wanted to show this one because this one's clearly, if Ravi is still on, this is one of our members who does narrowband imaging. So Jim, you want to mention this a little bit, or?
Yeah, so this in a lot of ways relates to, not as far as measuring shock waves or anything, but to the filters that Ravi was talking about. This is narrowband imaging and sulfur 2, hydrogen alpha, and oxygen 3. And it's a 2-panel mosaic taken with a 4-inch refracting telescope, monochrome camera, 3 narrowband filters that I just mentioned. And the narrowband filters are like, if you think of red as being 100 nanometers wide, this lets through like a 3 nanometer slit of hydrogen alpha and a 3 nanometer slit of sulfur 2, and the oxygen does the same thing. It's somewhere right on the border between green and blue. And I took these 2 images like 2 weeks apart. I was not planning a mosaic. I just happened to have the same camera rotation. I just happened to have enough overlap and was able to make a single image out of the Heart Nebula on the left and the Sol Nebula on the right.
Beautiful.
Is that the standard SHO palette?
Standard SHO palette, yes.
And your camera was not 300 megapixels.
Like 61.
Yeah, it's a full frame.
Yeah.
Monochrome. That's just gorgeous.
So what is the standard SHO?
So SHO is sulfur 2, hydrogen alpha, and oxygen 3. mapped to red, green, and blue respectively.
Okay.
And it's also known as the Hubble palette.
The Hubble palette, that's correct. Thanks, Wayne.
Yeah. The reason is because the other way is hydrogen in red.
Right, so there's several different mappings that you can do with narrowband. Like I've got an image of Cygnus loop that's in HOO, which would be hydrogen mapped to red, oxygen mapped to green, and oxygen mapped to blue. That's the other common one. And then you can mix up colors any way you want.
And to artistic effect, not for scientific reasons.
For artistic effect, yes. For entertainment value only.
Jim, from what location did you take these pictures?
In my backyard, Bordeaux 6. That's one of the beauties of narrowband. You know,
Exactly.
you just let through those tiny slits of light and it blocks out everything else. In fact, I believe it was the end of near one of these was near the middle of October, so I think it was like a full moon was around.
What was the total integration time for each of these?
I think about 2 hours each side, something like that.
Just 2 hours.
Wow. Nice.
That per filter or is that total?
I'll have to look that up real quick and then I'll jump back in later.
All right, so let's go back and go now. Steve, are you on?
Yes. Yeah, can you hear me?
Yes, sir.
Okay. Well, these are from several meetings ago. This is back in November when there was a very nice transit of Io across Jupiter. And I got enough images that I could put them together into an animated GIF file to make a nice little video there. But you can also see the storms in front of the red spot that are developing, and now they're even more prominent than they were then.
I see you've got a couple of moons to transit there, and
There's a lot of detail on Jupiter now.
Terrific. And then you had another one.
Yeah, I I like to see how far I can push things with my 14-inch here in our core observing area. And back in November, and since then, the weather hasn't been terribly cooperative. None of these nights were particularly good nights, but I managed to pick up Nereid, the 18.7 supposedly magnitude of Neptune's second satellite. This was over 4 nights.
Wow.
And in order to prove what you've got, you have to take a series of images and show that it was there one night and not there the next night. And that's not all that easy to do, to have a series of clear nights in succession these days.
Wow. Magnitude 18.7.
That's that's what it's rated at.
That's awesome.
Yeah. And that's sort of what Mount Palomar telescope was doing when it first started out. So it's amazing to be able to do this with amateur equipment now. But again, these are highly processed, highly stretched, as Wayne mentioned earlier, and highly contrasted. They're not beautiful pictures like the rest of you are showing.
Yeah. Cool though. Very cool. Thanks for sharing.
Sure.
If I could jump back in with those integration times. Sulfur was 2 hours, 40 minutes, Heart Nebula, sulfur was 2 hours, 40 minutes, hydrogen alpha was 5 hours, oxygen 3 was 2 hours, for a total of 9 hours and 40 minutes. The Sol Nebula was 2 hours, 40 minutes on sulfur 2 and hydrogen alpha, and oxygen 3 was an hour 40 for a total of 7 hours and 20 minutes.
Awesome.
Oh, goodness.
Awesome. And then this is just from the other night when we had the occultation of Mars by the moon, and these are from James Wellingham after he processed them. It's pretty cool. That's the ingress and egress photos. And I've got 2 videos of this just to show you how challenging it was to get that image. He also sent a, is this not going to work? He also sent a video of the, I don't know. I'll come back to that. Maybe I have it on and then oh, there it is. So here's the video of the egress where you can just see how terrible the seeing was that night. But he was able to process this. The other thing I like about this is that like the shadow of the moon is blocking like some of Mars right there. It doesn't now it finally looks like a circular cross section. So yeah, this is the raw data video that he used with Lucky Imaging to create that other image that we were looking at there. And you can really
On a shadow of the moon on Mars, it was the moon actually eclipsing? No, couldn't be. It would be.
yeah, that wasn't good point. That wasn't the shadow of the moon. That thank you.
It's the crater wall.
That was some kind of dark crater wall blocking the view. Yeah, thanks. That's much better.
And that's good evidence of why we put telescopes in space.
Yeah, right, exactly. That was this polar vortex thing has been awful for anybody trying to do planetary this month. Okay, next slide, we have Harini's video. Harini, would you like to talk to this if I can get it to work?
Yeah, so we had a few problems. My brother fixed it because the moon was moving and we were taking a time lapse. So we had to do the target correction. And there's this tiny dot. You can see it right next to the moon. And that's Mars. We took them in time lapse on our sea star, and then it's going behind the moon.
Did you stay outside in the cold with that, or did you
No, we
go back in?
No, we just put it outside, and then we sat inside with the iPad. We were looking at the iPad for the image.
Good for you. Well, I love this, especially looking at this compared to the video we just saw, because this really gives you a perspective for how small Mars is relative to the face of the moon. So thank you so much for sharing this.
Great job, Harini.
Yeah, that's
Thank you.
amazing. My God, that's awesome. Look at the color on the moon. I mean, that's just the moon is gorgeous, but to see it in time lapse with Mars approaching, that's just amazing.
Yeah, it really is. Gary is in the room.
Oh, yeah, thanks. So these were both taken with my Origin. The left, obviously, Triangulum. I think I did that no filter right out of the telescope. 2 hours of 10-second subs. The right Cygnus wall, I don't love that. There are too many artifacts in it, but I thought it was kind of cool. And it was actually one of 6 images that I took for a mosaic of the North American nebula. So this was just a little bit more processed. I'll get better at it. So
is that an SHO?
Sorry?
Is that an SHO or is that color? Was there a one-shot color camera or?
No, it's an integrated camera with an Origin Smart Observatory. So it's all integrated in one unit.
Oh, okay.
It's the Celestron version of the Sea Star.
Got it. Yeah.
With a bigger aperture.
But does it actually have filters built into it as well?
No, but it has a filter tray.
Okay.
And I can
I was just wondering about the
there was just a it's a process, so it has a clear filter that I have to use, but there are narrowband filters you can.
You could, but, so that was just.
That was just clear. Yeah, yeah.
It's cool. It almost looks like it's narrowband and processed.
Yeah,
Yeah.
I'm used to that. Well, actually, even there, you can see the Cygnus wall looks more reddish. Usually the hydrogen kind of dominates.
Yeah.
Yeah.
So this was, over 2 nights, I took, 6 1-hour, imaging sessions to get as much of the North American nebula as I could. These were, because they were taken over 2 nights and the conditions were a little bit different. I again, don't love this, but I was really focused on, could I even do this with that telescope, much less focus on the quality of the image. But the quality of the image came out okay. This is essentially what comes out of the scope with no post-processing whatsoever. And I cheated. I pieced the 6 images together actually in PowerPoint, which was trickier than I thought it was going to be, because I had to rotate the images and I had to adjust the transparency to try and get them about the same darkness. And so anyway, I'll get better at this. My next attempt, I think, will be the Cygnus loop. I'll try something like this with that next.
Cool. And this was at Alpha Ridge, Bortle 5?
No, I took this from my driveway.
Oh, wow.
Bortle 7.
Wow, that's even more impressive. All right, cool. And then is Michael Connolly on? This looks like some C-star
everybody.
images. Yes, go ahead.
Yeah, so the past year I've been really playing with the C-Star S50, and so these are 3 that I was able to take over pretty much Christmas break, and I got a little bit of using the mosaic options that are with it. I got the horse head there with the flame nebula on the left. First time I've been able to get a camera and scope that can kind of get almost all of Andromeda, so I was pretty happy with that one in the middle. Because usually I just kind of get like different pieces. And then I got a little bit of the Running Man there with Orion, and I thought they turned out pretty good with just the pure mosaic options out of the S50. And this is all from my house in Westminster, really outside my driveway, and I've got a wonderful neighbor that keeps a spotlight on. So I thought these turned out pretty good.
Wow, that's just amazing that a C-star can do this. I'm thinking of like the first photographic plate images of Hubble that but that's incredible. I mean, of the Orion Nebula, incredible. Thanks for sharing those.
Yeah, thank you.
And then Wayne.
Yeah, this is a group of galaxies in the constellation Aries. The barred spiral galaxy up in the upper left is IC 167, and it's about magnitude 14.
This
And
looks like what you showed a few months ago.
I think I showed a preliminary version. I've added data. I added data to it.
This looks brighter.
Yeah, I added data to it. So I more than doubled the exposure time, I think. So it does look brighter. And of course, it's different processing.
I wish I would have remembered that. I would have showed the before and after next to each other.
So, and then over on the right is, let's see, NGC 678, which is magnitude 13.3, that edge-on spiral galaxy. So it was just an interesting grouping of galaxies. I was looking for something to image. I pulled up a field of view of something I thought I might want to image, and I saw this off to the corner, and I thought, hey, let's look at that. So I looked at this instead.
Beautiful.
So this is 10 hours and 44 minutes of exposure time from Alpha Ridge Park.
With your 8-inch RC?
Yes.
Awesome. Awesome. And then we're back to the last slide, which is Jim's. So we're finishing up right around 9 o'clock, which is good because we don't want to make the Robinson Nature Center people stay any later than they have to. Does anybody have is Ravi still on? Does anybody have any other questions that they thought of? Ravi's still here. That's fantastic. Well, maybe we can communicate it to you via email if somebody comes up with something. Other than that, thank you guys so much for attending the meeting. I'm excited for HAL in 2025. I think we're going to do fun stuff. You know, what I didn't do, what I always do, what I did last year when I did the treasurer's report is I did a little year in review of like all the outreach and educational stuff we did. But I didn't put that in this because I was a little pressed for time today when I was finally wrapping this up. But we did a lot of really good. We had a lot of engagement, a lot of members of the public at our star parties, 200 plus people often, and so I'm hoping that we do a lot more of that, and that 2025 will be even better. So thank you all for being here, and thanks for being part of
And
HAL.
Victor, I put a chat there for you in the group if anybody's interested for next month.
Okay,
For
sounds good.
the
Thanks for-
soon to be
Oh.
solar polar flip.
Yeah, we haven't heard from you about this, what's going on with the sun lately. Oh, and everybody here in the room, please come by and get a business card, or if you want to grab a few.
Bye,
Yay,
everyone.
Go Hal.
Bye.
See you later.
Yeah.
Bye.
Thank you, Dr. Sankrit. That was awesome.
Thanks. Bye.
Thank you, everybody.
Thank you. That really was cool. Thank you
Don't
so much.
forget to stop recording.
No, yeah, thank you.